Given k-sorted linked list, how do you design an algorithm to merge all of them into one simply sorted linked list and return? That's about today's video. Let's dive in. San Francisco Bay Area, or Silicon Valley. This is where my dream started. This is Steve here. Today we're going through LeetCode problem 23, merge k-sorted lists. But before we dive in, just do me a favor and smash the like button and subscribe to my channel as we continue to go through all of the LeetCode problems and will help people to prepare for software engineering interviews. Today, let's right now start diving to this problem. This is a very classic and very useful problem that just in case if you encounter in your real interview, after you watch today's video, you'll have a better idea, understand how to go through this and walk through the problem along with your interviewer. And if you do land a job, if you can understand the data structure that we will go through today, it will help a lot in your day-to-day work. So with that said, let's take a look at this question. It's asking us to merge k-sorted linked lists and retain it as one sorted list. And then second question is to analyze and describe its complexity. We're given only one example. That's good enough. So this input is there are three sorted linked lists: 1, 4, 5, 1, 3, 4, and 2, 6. And the output is all of them sorted, but it's returned as one singularly sorted linked list. So 1, 1, 2, 3, 4, 4, and 5, 6. Let's think about how we can tackle this problem if this is the very first time that you get asked during a real interview. What would you do about it? Let's just start with intuition first. Forget about there are k-sorted linked list. Let's just take this simplest example. Say there are, can I copy it? Okay, yes, I can. But its font size is too small. Let me change it to bigger. Okay, so this is the simplest case. No, actually, simplest case is going to be, I'll just call it, let's say we have two sorted linked lists. How do we merge them and combine them into one sorted linked list? Result should be, let's call it 1, 2, 4, 5, and 6. This is the result. This is the result that we are asked to return. How can we handle this case? Just forget about the k-sorted linked list. Let's assume there are only two sorted linked lists right now. How do we handle this? Easy case, so that we can have a better intuition. Then we can based on our intuition, we can derive a better and more generic solution to handle k-sorted linked list. That's the idea. Let's think about it for 1 second. Well, what I would do is we can have two pointers, like say P1 pointing to the head of the first linked list and P2 pointing to the head of the second linked list. Why do we want to do that? Because we want to, so first remember the feature of the given linked list is that they are, every single one of them, they are individually sorted, right? So say this one is sorted. So that means we can, in order, go through every single one of them. Because we don't need to worry about we might encounter someone here which is actually bigger than the one that is after him or smaller than the ones that we have gone through, right? So we can use one pointer starting from the very left of every single sorted linked list, and then we'll just keep comparing the head of every single sorted list. I hope you are still with me at this time. So let's just go through this example. Say here is P1. We have a pointer called P1 is pointing to the head of the first linked list, and P2 is pointing to the head of the second linked list. We compare P1 and P2. So P1 is 1, P2 is 2. So 1 is smaller than 2. Let's remove this. So now we know 1 is smaller than 2. We'll just put 1 first and 2 Oh no, we'll just put we'll initialize a container, say an array list or a linked list or whatever. For now, that doesn't matter. So right, we'll just put 1 into the result, into the holder, into the container, right? And now we'll increment the first pointer by 1. So P1 is going to be pointing to the second node of the linked list. Why do we do that? Because we have already gone through, we have already merged the first node into the final result. So at this point, the P1 is pointing at the second node of the first linked list, and P2 doesn't move. Why? Because the node that P2 was pointing to is bigger than the other node. So this one didn't get merged in yet, right? And then we'll compare, suppose there are only 2 linked lists, we'll compare P1 and P2 again. That compare the value of the nodes that these 2 pointers are pointing at. So at this point, P2, the node that P2 is pointing at is 2, which is smaller than the node that P1 is pointing at, which is 4. So we know at this point we want to merge 2 into the final result, right? So just as what we did with pointer 1, after we merge this node, we increment this pointer 1 by 1. So we're going to do it here. We're going to increment this P2 by 1. Then P2 is pointing at 6, right? We'll continue to do this. Now we'll compare the 2 nodes that P1 and P2 are pointing at. So now it's 4 and 6. We'll compare 4 and 6, right? So 4 is smaller than 6, so we'll merge 4 into this linked list. And then we'll, as just we did both times for these 2 pointers, after we merge the one that the pointer is pointing at, we're going to increment this pointer by 1. So now P1 is pointing at 5. And P2 didn't move because we didn't merge the one that it was pointing at. So now we will just, for the simplicity of this very simple use case, test case, we compare the last 2 nodes of P1 and P2 they are pointing at, 5 and 6. So we know 5 is smaller than 6. So we'll merge 5 here. And then P1 will continue to increment it, which means it's pointing at it's pointing at the outer boundary of the first linked list already, which means we have gone through the first linked list already. Since there are only 2 linked lists here, then we'll just safely merge whatever that is left over at P2, right, which is 6. So we'll put 6 here, and then we increment P1 by 1 as well. So then next time we know P2 is also pointing at outer boundary of the second linked list. That's it. We're done with merging the 2 sorted linked lists into 1 simply sorted linked list. This is the result, right? Looking correct. So take one step back. How did we do this? First, we used 2 pointers, right? We used 1 pointer for each simply sorted linked list. And second is that every single pointer that we initialized, we used, is starting from the very left end of the simply sorted linked list. Why? Because every sorted linked list is sorted. That's how we can do it this way. So how can we build a solution based on top of this intuition? Well, I would say it's pretty intuitive or straightforward. If there are, say, if there are k sorted linked list, what we can do is to use k pointers, right? I hope you guys are still with me. We can, for every individual sorted linked list, we're going to use a pointer to start from the very head of the linked list, and we'll just compare all of the k hats. Instead of comparing 2 hats, we'll just compare all of the k hats, right? Because every single hat is guaranteed to be the smallest of the node that we are going through. So we'll just compare the hats, all of the k hats. Then we know the current next one that we are about to merge into the final result is going to be the smallest out of the k hats, right? That's the intuition. That's the solution we're going to build out of this intuition. Very straightforward. And then second question that comes into play is there any data structure or any algorithms that we can take advantage of to quickly get access to the smallest item out of k items? Well, I would say if you learn a data structure in your data structure and algorithms computer science class, a very good data structure that should come into your head is heap, min heap. It's basically a binary tree with the smallest node, with the node with the node with the smallest value is at the top of the tree, which is some people call it the root of the tree, right? We can take advantage of this data structure, min heap, to get very fast access to either enqueue or dequeue an element out of this k items. That's the idea and the algorithm. I think if that's all clear, we can start writing code. Of course, we'll go through the time and space complexity for sure after we write the code. Now let's think about how we can write the code. First, we'll have a priority queue. It's going to be list node. We'll call it heap. New. Let me copy this word too long. We need to initialize a customized comparator. This is how we do that in Java. Different languages might have different ways, like even some languages might have built-in functions you can just utilize. Comparator, and then it's going to be a list node. How we're going to compare nodes is going to be based on their value. We'll use O1 and O2 to compare them. Just simple based on their value. O2 val. See, whichever one is bigger, we're going to use that one as the next one that's going to be popped out of the heap. And then we're going to initialize this heap. List hat lists. Well, what we'll do is first we'll just check just in case anything could happen. If hat is not equal to null, we'll just put that into the heap. Offer heap hat. We'll offer the hat into the heap. And what else? So now we have built this heap. What we are going to do, so just to step back 1 second. So this is what we have done is to initialize a heap, and then we are given the hat of all of the sorted linked list, and then we'll just we'll just enqueue all of the hats, all of the k sorted linked list hats into this queue. That's what we did with this for loop. Next step, we're going to just pop every single smallest element out of this heap and add that into the final result. The final result, the return type is a list node. So we're going to initialize a list node, new list node. We'll call it -1. And then another common technique which I use, up to you how to use it. This is the way that I do. Just initialize a dummy node, and in the end we're just going to return pre.next. That's it. And then so here we're going to use a while loop to go through every single one of the k sorted linked list, while heap is empty. While heap is not empty, we're just going to pop it out. So we have built this customized comparator, which is guaranteed to give us the smallest element in the heap. So we can just simply pull it. Current heap pull. So at this time, what we'll do is we'll just assign. We'll just create a new list node. with current value to temp next. So this is appending, we're creating a new list node. So let's say here, this is the one that we get 1 and 1. We'll create a new list node and append it to temp.next. This is what we're doing here. And then, as I said here, the P1 used, the first pointer used to be pointing at the first one, right? After we pop it out of the heap and add it to the final result, let me remove this, and add it to the final result, what we want to do is to increment this pointer by 1, so to move it to the next position of this pointed at linked list. So here what we're going to do is to check if, just in case if current next not equals to null, then we can just add offer. We can just add current next into this min heap, and then we'll just continue to iterate through temp next until we finish iterating through every single sorted linked list, because this one is we are moving the pointer at the final result towards the right as well. This is the algorithm. Let's hit submit. Let me just double check. Heap lists, heap head. That's correct. And then there's heap here. We pull it, check whether it's not empty. We assign it. Things are looking good to me. Let me just hit submit button and see. Alright, it's accepted. It's accepted a few seconds ago. Then this is the result. It's accepted. Now let's talk about the time complexity and space complexity of this solution, as the problem is asking us analyze and describe its complexity. I'll put it out here first. The time complexity is O n log k, where n is there are a total of n nodes in all k sorted linked lists combined, and k is just the number of sorted linked lists that were given. Why it's O n times log k? Because this is the fastest, and of course for sure across all the solutions, the algorithms that we can come up with for this solution. Why it's log k? Because we used a priority queue, a min heap, a binary tree. Let's do a quick search by PriorityQueue Java doc. Let's see. PriorityQueue Java doc. Let's look at the latest doc, Java doc, and we'll understand what that means, log. So here, we see we're looking at a class, PriorityQueue Java. This is Java language built-in class, shipped out of, I don't know, maybe, yeah, since 1.5, since Java 5. We have this class implemented, shipped with Java language. So implementation node, we see this implementation provides O log n time. This n is the total number of elements that's put or pulled out of this queue. So in our context, this n is just the k, right? Because we always put a total number of k elements, k linked list nodes into this min heap. So for our context, this is the number k. So this implementation provides O log k time for enqueuing and dequeuing methods, which means offer, pull, and remove and add. Which we used, the ones that we used are offer and pull. Let's take a look at our code again. First, we use offer. This is costing us O log k time, right? Because there's a total of the length of this list is k. So we go through this call at most k times if all of the heads are not null, right? And then we pull. We'll have to at least go through this k times as well, because there could be k linked list heads in this min heap. So we use pull here, and so we use the two APIs that we call for this min heap is pull and offer, which is enqueue and dequeue in other context. So here we are looking at the Java doc implementation. This implementation provides O log n time for enqueuing and dequeuing. So that is where this O log k comes into play. Let me highlight that in, okay, this is too bright. This is where the log k comes into play. Then where is the times n come into play? Think about this code. Let's go through the code again. We say n stands for there are a total of n number of nodes, right? So we're given, say, in this, for example, in this example, there are a total 3 plus 3, 6, 6 plus 2, 8. There are a total 8 nodes. So n equals to 8, which means here, n equals to 8. 8 times log 3, right? Because k equals to 3, there are a total of 3 sorted linked list here. Why it's n equals 8 here? Because every time we have to, from the beginning to the end, before we could merge a completely merged one sorted linked list with every individual linked list merged into this one, we'll have to go through every single node at least once. Or we actually just go through them once, right? Because we have to visit every single node. Otherwise, we have no way to know where this linked list node should end up being in the final merged linked list. That's why we have an n here. And every node has to go through the min heap, right? That's where the time complexity, that's the upper bound of the time complexity. That's it. I hope you guys are still with me. And then let's talk about space complexity. Space complexity is just O log k. This is very optimal already. You can, like other algorithms, will just go far above this, or will just go above this. But for this algorithm that we come up with, we use a min heap to always enqueue the head of every single linked list into the min heap. The extra time complexity we're going to consume is only OK. Of course, we're going to ignore the final result, which is going to be On. That's the result. It's not the extra memory that we will consume along the way during our computation, right? So what is OK? As we said, K is the number of sorted linked list. So looking at it, thinking about our algorithm again, we created a min heap and we put all of the heads, right? This is the head pointer, head pointer, head pointer. Although we continue to move the head pointers towards the right of every individual sorted linked list, we always put only the head list nodes into the min heap, right? So that means at max, at any point of time during our entire algorithm, there is at max k list nodes in our min heap, right? Because we're given only k sorted linked list. Sometimes, like, there are shorter ones, so like this one, it runs out, we might end up having k minus 1 linked list nodes in our min heap. But our upper bound of space complexity is OK, because say at the very beginning, we have all 3 sorted linked list head nodes in our min heap. That is the space complexity. As I said previously, both in terms of time and space complexity, this algorithm is the most efficient. All in sum, this problem gives us a very good practice opportunity to understand what is PriorityQueue, and say in Java how to implement a customized comparator and the basic operations of linked list. These techniques, how to use a pre-head node and a temp head node to go through to create a new list node and append it to the next, and then finally return pre.next. I would say this is a very golden opportunity or golden questions, at least a couple years ago. Interviewers get to ask this question for candidates a lot, because it's a very good chance to help the interviewer to gauge a CS students or in software engineers who worked a couple years in industry to understand their understanding of the basic data structures and how they handle all of the corner cases. Say you have to handle whether the list node is null or not. Again, that basically concludes the tutorial of this LeetCode problem. I hope you guys feel you learned something from it. If you do, don't hesitate to tap that like button. That's going to help a lot with the YouTube algorithm. And don't forget to subscribe to my channel. Alright, that's it. I'll see you guys in the next video.